Whoa, don't be scared off by the big image. Welcome to week 2 of Learning at Home for Specialist Maths. Today we're having a look at exercise 8D, equivalent statements. Let's have a look at the key ideas. I'll do a few worked examples, then you should be right to get stuck into the exercise. So we already know about Pythagoras' theorem here. We're looking at a statement and its converse, not the shoes, but converse of a statement. So here's a statement. If the angle between A and B is 90 degrees, then we know that A squared plus B squared will equal C squared, assuming here we're talking about a triangle with sides A, B, and C. Yes. The converse of the statement, if A squared plus B squared equals C squared for that given triangle, then the angle between A and B must be 90 degrees. And in this case, both of those statements are true. We can have true statements and false statements for statements and converses. We'll have a look at the cases of each. Here's another example. If it is raining, then there are clouds in the sky. That is, although some people might like to argue it, it's probably true. You can't have rain without some clouds dropping the rain. So that's fair enough. However, the converse, if there are clouds in the sky, it is raining. Well, that's just not true, is it? So sometimes they will be true, sometimes they won't. The main bit you get out of that, when we switch the hypothesis and the conclusion, so instead of P implies Q, we can obtain the converse Q implies P. Equivalent statements are statements such as the following. If P is your heart is beating and Q is you're alive, P implies Q and Q implies P. If your heart's beating, you're alive. If you're alive, your heart's beating. You could break it down to fractions of seconds and say it wasn't beating at that particular second, but you get the idea of it. These are equivalent statements, and the other way we talk about these is if and only if. You'll sometimes see that written as IFF for if and only if, just a shorthand way of writing that. And to prove equivalent statements, you have to prove it in both directions. I'd have to prove P implies Q, and I'd have to prove that Q implies P, and we're going to look at a couple of examples of those today. Again, there's a little summary of what we're talking about. It's really just the converse. If I have P implies Q, the converse is Q implies P, and equivalent statements, P implies Q and Q implies P. Let's have a look at example 15 here. X and Y are positive real numbers. Consider the statement, if X is less than Y, then X squared is less than Y squared. Write down the converse. Well, it's if X squared is less than Y squared, then X is less than Y. That's the statement we can go with. I've got to go answer a phone. I'm just going to pause there. It won't take as long for you as it will for me. Oh, that's more work for me. Don't you love answering the phone? That Y squared looked a bit grubby. Let's fix that up. All right, let's go from there. We're going to prove this converse statement. So we're going to try and prove that if X squared is less than Y squared, then X is less than Y. 4 positive real numbers, X and Y. So let's start with the statement. X squared is less than Y squared. So a good way to show that X is less than Y would be to show something along the lines of X minus Y is negative or Y minus X is positive. Something like that would be a good way to do it, wouldn't it? So if I'm trying to show something positive or negative, I think we get everything on one side is probably going to help us. So let's go with X squared minus Y squared is less than 0. Okay, well, good news here is I've got my favourite rule in maths and I'm going to use it, aren't I? X squared minus Y squared I can rewrite as X plus Y multiplied by X minus Y. Now, for this to be less than 0, we know that both X and Y are positive real numbers. So X plus Y must be positive. So for this statement to be true, it must be that X minus Y is less than 0, which is equivalent to saying X is less than Y. And we finish off that proof. Nice little one there. That's another technique you can use. Trying to show that something is smaller than something else. Easy way to do it is to show that the difference is negative. All right, let's have a look at example 16. M and N are integers. Consider the statement, if M and N are even, then M plus N is even. Write down the converse of this statement. So it would be, put them in the reverse order. If M plus n is even, then m and n are even. All right, show that the converse is not true. This is an easy case of proof by counterexample. All you need is one counterexample and you can take down an entire proof, which is very handy. So if I can find two numbers, m and n, that are integers that are not even, and show that their sum is even, I'm as good as then. As good as done. Let m equal 3 and n equal 1. Therefore, m and n are odd, but m plus n equals 4 is even. So I've shown the converse is not true. Therefore, the converse is false or not true. They use not true, so I'm going to use the same. Pretty easy, that one, isn't it? So if m and n are even, the sum is definitely even. That's true. If m and n are if m plus n is even, it doesn't follow that they have to be m and n individually even. They could both be odd and it would work. Question example 17 here. Let n be an element of z, so it's an integer. Prove that n is even if and only if n plus 1 is odd. So I have to do two things. I have to do p implying q, and I have to do q implies p. That's the structure of the argument that we're going to have to form here. So I'm going to start by saying, let's assume that n is even. So let n equal 2k, where k is an integer. That's how we show that it's an even number, okay? Show that if that is even, then n plus 1 is going to equal 2k plus 1, which is our definition of an odd number. So it's true that if n is even, then n plus 1 is odd. Now we have to do the opposite. Let n plus 1 be odd. Therefore, n plus 1 equals 2 times k plus 1 for some k element of z. And I'm trying to show if n plus 1 is odd, then n is even. So by subtracting 1 from each side, I'm going to get n equals 2k, which means n is even. So I've shown p implies q and q implies p. Therefore, I have shown that if n is even, I don't need the if at the start, I need n is even, and I should probably keep if and only if, and I think it should actually have a comma like that if you're going to do that, if and only if n plus 1 is odd. And there you've got it. You proved it in one direction and then in the other direction, so you are safe to go. Underneath here, I'm going to fill in the little exercises. You can probably work through all of exercise 8D. There's not too much to do there. These questions below, that's an extra skill sheet. I will leave that in there because I think they're good questions to have a go at too. That should be enough for 8D. I'll catch you in the next video. Good luck, guys. See you next time.